You typed one command and a model with billions of weights answered, locally, offline, on the machine in front of you. Here is the trick that makes that fit. The trick behind Ollama Run. Start with why fitting is hard at all. A model is, physically, just billions of stored numbers. So the question of whether it fits is a question of bytes. Each weight is normally stored in half precision, 2 bytes. So even a small 7 billion parameter model weighs 14 gigabytes. Before it does a single thing, more than most laptops will happily hand to one program. And the bytes hurt twice. To generate each token, the chip streams essentially the whole model out of memory, and it spends most of that time waiting on the stream, not computing. So the bytes set the footprint and roughly the speed. Shrink the bytes and you shrink both what it fits on and how fast it types. So the real question is how few bytes a weight can survive on. Here is the saving grace. A trained network's weights came out of a noisy process. Gradient descent on shuffled batches from a random start. The 7th decimal place of any single weight is basically noise. What the network actually leans on is the collective pattern across millions of weights working together. No single weight is load-bearing, so no single weight has to be exact. Quantization takes that seriously. Store each weight in 4 bits instead of 16. Accept a small rounding error on everyone, and bet the predictions barely move. Remarkably, the bet pays off. Watch what rounding actually does to the weights. Take a small slice of one weight matrix and lay its values on the number line. In half precision, each dot can sit essentially anywhere, a smooth continuum of positions. 4 bits allow exactly 16 positions. These gold markers are the entire vocabulary the format can express, and every weight has to become one of them. So every weight snaps to its nearest marker. That snap is the whole algorithm. Everything after this is just bookkeeping around it. The snap is not free. Every dot moved a little, and the highlighted ones moved most. That movement is the rounding error, and the entire game is keeping it small. The bookkeeping turns out to be 2 small numbers. Here's the entire recipe. Divide a weight by a scale, round to the nearest integer, shift by a 0 point. That little integer q is what actually gets stored. The scale s is the width of one bucket, the range, the weight span divided by the number of gaps the bit budget allows. 2 to the b minus one of them. The 0 point z pins real 0 onto one of the integers, because zeros are everywhere in a network and deserve to be represented exactly. At runtime, the model multiplies back, s times q minus z, recovering the nearest bucket center. The only overhead is those 2 small shared numbers. Now stack that saving up and ask the real question. Line up the same 7 billion weights at different precisions. Full precision, 32 bits, would be 28 gigabytes, which is why nobody ships it. Half precision halves that to 14, the usual starting point. 8-bit integers halve it again to 7, and 4-bit integers land near 3.5 gigabytes. That last column is where the models you run locally actually live. Put the before and after side by side. So take that latter to a real laptop, 16 gigabytes of memory. At half precision, the weights alone are 14, eating almost the whole machine before you say a word. And generation needs its own working memory, the KV cache plus overhead. Ask for that on top of 14 gigabytes of weights, and there is nowhere to put it. It stalls. Now drop to the 4-bit rung. The weights collapse to about 4 gigabytes. The cache sits comfortably beside them, and the whole thing runs with room to spare. That is the moment Ollama Run just works. This all sounds free. It is not quite. Before quantization, the ledger reads like this: 14 gigabytes on disk, closer to 18 once you add the working memory to run it, and the whole 14 streaming through the chip for every single token. Quantize to 4 bits and watch every number fall. The file drops to about 4 gigabytes. It runs comfortably in 6, and only a quarter of the bytes move per token, which is why it usually types faster too. Most of that damage comes from one place, and it can be contained. But there is a wall, and it is worth being honest about. 8 bits is the comfortable floor. Across most models, the quality drop hides inside measurement noise, which is why 8-bit is routine. 4 bits usually cost something real but small, a point here and there, and the gap keeps shrinking as formats and calibration improve. For running locally, it is the current sweet spot. Push toward 3 and 2 bits and the rounding errors stop averaging out. Quality falls off a cliff and turns model dependent. The honest rule is to test on your own task, because benchmark averages hide exactly the failures you would notice. And you have already been running exactly this. Look back at the number line. Real weights bunch up near 0 in a bell, so a tight ruler gives the crowd 16 fine levels, and the rounding error stays tiny. But once in a while a single weight sits far from the crowd. One lonely outlier, way out here, and the scale is set by the range. To reach that one outlier, the whole ruler has to stretch, so every bucket in the crowded middle gets wider, and the millions of weights that actually matter suddenly round coarsely. One weight degrades a million, so the fix is smaller rulers. Give each little group of weights its own scale, and the outlier only fattens the buckets of its own group. The crowd goes right back to rounding finely. That is per group quantization. One line to take away. Here is the payoff. Those model files you pull to run locally, the GGUF files behind llama.cpp and Ollama, are exactly this lesson. Weights snapped to a handful of bits and stored with per group scales. The tag most people never think about, something like Q4KM, is the scheme. 4-bit weights with a smart mix that keeps the most sensitive layers a little higher, which is why it is the sensible default. And at runtime, the integers unpack back to full precision for the actual math. Only the storage and the streaming shrank, and the streaming was the bottleneck all along. That is the whole trick. Quantization stores each weight in a few bits by snapping it to the nearest level on a shared ruler. A 14 gigabyte model becomes a 4 gigabyte file that fits an ordinary laptop. Generation speeds up because fewer bytes stream per token. And with per group scales and bell-shaped formats, the quality barely moves. It is why Ollama Run puts a frontier scale model on the machine in front of you. Big model, small machine.